Assalamualaikum and a very good day to our lecturer, Madam Norzila binti Musa. We are Group 2 and today we are proud to present our group project, the LOOPIFY music player. Before we begin, let me introduce the team behind this software. I am Saiful IKRAM, the project manager and lead for File I/O. Joining me are Muhammad Danish Haikal, who handled testing, bug fixes, and the task metrics. Next, we have Muhammad ZULFARHAN, who developed our audio engine and timers, and Danish, who designed our GUI architecture and layouts. Moving on to the introduction, the primary objective of this project is to develop a GUI-based application that solves a real-life problem. Our problem statement focuses on modern audio players such as Spotify or VLC. These commercial players are resource-heavy and require an internet connection, making it difficult for developers to integrate a lightweight audio player into other desktop software. Additionally, users frequently face the issue of losing records of their frequently played songs because many simple players lack a history logging system. To solve this, LOOPIFY serves as lightweight office alternative design to manage and play local legacy audio files efficiently.
For our application's concept and visual team, we decided to adopt a premium Apple Music dark mode aesthetic. The master canvas used a pitch OLED black background paired with elevated dark grey panels. We chose this dark color scheme specifically to reduce user eye strain during extended usage. To balance the dark theme, we applied a vibrant Apple Music red as our primary accent for buttons and sliders. This creates a dynamical visual contrast that symbolizes musical energy and guides the user's eye to interactive components. Now, let's look at the actual structural components and layouts used to build our GUI. As shown in the table, we broke down our application into structured layers. First, the JFrame serves as our master window canvas. To organize the space, we applied a grid layout with a 5x1 matrix as our master layout manager. This perfectly segments the windows into 5 equal vertical rows. Inside each row, we place a J panel to act as individual structural containers. To arrange components inside these panels, we use nest layouts. We use flow layout to naturally position our media control buttons and file selection tools side by side. Meanwhile, border layout was implemented in the progress and status bus to snap the timeline elements and system status text cleanly to the edges. Finally, we wrap every single panel in a title border to give the interface a clean boundary and a highly organized visual flow. This is our visual blueprint, showcasing how the 5 nested layouts structured our applications when launched. First, at the very top, the title banner handles our branding alignment. Second, the file selection layout organizes our browsing tools and history tracking side by side. Third, the media controller panel centralizes our high contrast red playback buttons. Fourth, the audio progress layout locks the timeline, slider and monospace clock cleanly at 0. Finally, the status display at the bottom outputs a live system confirmation message. Together, these 5 distinct zones create a highly uniform, clean and balanced interface layout.
To address the history logging issue, we implemented specific functional requirements for file management and persistence. As you can see in the interface layout, we utilize 3 main components. First, we use a JFile chooser to integrate the system native file explorer, allowing for intuitive audio selection. Second, for persistent data storage, we utilize buffer reader and buffer writer to actively track and save the user's listening history. Finally, we integrated a JCombo box to enable active list management. This allows users to execute load selected or delete commands directly from the GUI, which updates the history text file in real time. Here is a look at the backend implementation for this feature. This code snippet demonstrates how we set up the file selection and history operations. We initialize a JPanel with a flow layout to align the components neatly from the left side. You can see the instantiation of the JCombo box for the history dropdown. alongside the respective buttons for browsing new files, loading save files, and deleting history. This structure ensures our persistent logic is seamlessly connected to the user interface.
While the engine handles the sound, the synchronization logic ensures the user interface stays perfectly in step with the audio. So firstly, we have a dynamic background tree. To keep the GUI update, we use a dynamic background tree powered by a Java strings timer. This timer ticks every 100 milliseconds, holding to playback data to ensure that what the user sees on the screen is perfectly synchronized with the audio execution in the backend. Second is time unit conversion. The raw data from the audio file is measured in microsecond, which is very user-friendly. We implement time unit conversion to translate those microseconds into milliseconds for the J slider position. We also use string format to render the data into a clean, readable digital display in the standard minute and second format. Third, we have interactive scrubbing. Finally, to give the user full control, we have interactive scrubbing. We implemented a chance listener that detects when a user drag and drop the seeker slider. Once the user moves the slider, the system uses the second microsecond position method instantly and smoothly relocate the audio track to the desired point. Now we go to the core functional requirement that power of the audio playback engine for this application. So we have a key component. The first is Java Sound API. At the foundation, we utilize the Java Sound API by integrating the clip and audio input stream class. The system is capable of loading and reading legacy audio format, especially WAV, AU, and MIG files into computer memory stream for high performance playback. Second is playback control logic. For the actual user control, we have implemented seamless playback logic. The play function invokes the audio clip start method to play a track once. We also include a loop function which uses the loop continuously, constant allow for uninterrupted repeat playback. Third is resource management. Efficiency is the key in audio processing. Our resource management ensures that when the stop function is called, audio clip close is triggered. This does not just stop the music, it flushes the audio line cache and free up system memory to prevent lag and ensure overall application stability.
Now let's look at the file selection feature. To load a song, simply click the Browse New File button. When I click the Browse New File button, the program triggers our custom JFile chooser dialog. From here, the user can easily navigate their PC directories and select a .wav file, which is then safely loaded into our backend system. All of the music can be saved in the file chooser so that when you open it again, the music doesn't go. Now I will demonstrate my specific feature, the history log. To prove that the data persists, I will close the application completely and run it again. As you can see, by simply opening the Save drop-down menu, I can instantly find and load the song we just played without having to search my computer again. If I want to clear a track from my history, I just select it and click the delete button, which permanently removes it from the log.
Next, for main output, active media playback state. This is the phase where the audio track is actively playing. As the audio engine developer, I want to highlight the three components provide that my backend audio logical successfully driver the front UI. The first is the J slider progress bar. When the audio engine execute play audio, the background timer automatically update and move this slide handle every 10 ms. Second is the digital time tracker. The time display on the right update in real time, showing that my mathematical conversion from microsecond to minutes and seconds is working flawlessly. Third is the status bar. The status text at the bottom dynamically switches to playing along with the song title, confirming that the audio data stream is running smoothly without any crash. So in summary, output 2 provide the audio engine and GUI component are perfectly synchronized. That's it.
We focus on advanced features and crash prevention. We introduce a unified dynamic play and pause button that instantly swap icon while bookmarking playback timestamp. More importantly, let's look at the crash prevention logic for our delete button. Before improvise, the system suffered from a major error if a song was actively playing and the user clicked delete to remove the exact trackpad from the history dropdown. The background threads will instantly lose its file. This results in an immediate system freeze or a server null pointer exception crash. After our improvisation, we injected defensive validation logic. Now when the delete action is triggered, the backend instantly checks if the targeted track is the one currently playing. If it matches, the system safely execute stop audio, flush the active memory reference and cleanly update the UI dropdown. The application now runs seamless without any crashes. Now, let me fully demonstrate how a user select and listen to a song using LOOPIFY player. The process is smooth and divided into 3 simple steps. For step 1, loading the audio file. To start, the user clicks the browse button in the file selection panel. This opens a file chooser filtered strictly for WAV or MID formats. Once the track is chosen, the file path is immediately added to our history list and saved permanently into our background database text file. For the steps 2, initiating playback and visual tracking. Next, when the user clicks the play button, the backend initializes the audio stream clip. Instantly, our real-time progress timer kicks in, causing the slider to move smoothly and the monospace clock to start counting up from 0 to show the track duration. For last step, interactive control and continuous loop. During playback, the user can click pause at any time to freeze the audio and bookmark the exact timestamp, or hit play again to resume seamlessly. If the user wants the song to play continuously without stopping, they can toggle the loop button, which commands the system to auto restart the track from the beginning every time it's reached the end. As you can see, the entire cycle from loading to looping runs perfectly, providing a responsive and crash-free listening experience. In conclusion, LOOPIFY player successfully bridged interactive GUI layouts with persistent file I/O management under solid OOP principles. The application delivers a highly stable dark mode audio player that retains user track histories across sessions. Backed by defensive crash prevention logic, the system completely eliminates memory runtime errors during active track deletions, ensuring a smooth and reliable user experience. This is all from us. Thank you.